Morning. This is going to be a brief lecture on linearity, reviewing linearity. We've already talked about linearity, but I wanted to show you this one kind of an interesting, maybe a unusual application in which we can use linearity to solve for an unknown. So before going on and doing the problem, let me first remind you what linearity means. Okay, so you might know this from other courses, but basically, if we have a system, so let me mark that by just drawing a box, okay, with input and output. Okay, we have a system that has an input X and output Y. Okay. Then, if we apply to the input a scale version of the previous input, we should get a scale version of the previous output. Okay, so this is for A equals constant, right? So if you have a system with X in and Y out, then if you scale the input, if you get a scaled output, then this system has what's called the multiplicative property. So this is the what's called the multiplicity. Okay. Then there's one more property. Okay, and systems that have both these properties are called linear systems. So the other property is, it goes like this. So suppose we have this. Again. Let's do the same system again. So we have a system S. Let's put in x1, and suppose the output in that case is y1. And suppose we also put in another input x2, and suppose that output is y2. Then, if the system input is replaced to ax1 plus bx2, in other words, instead of applying x1 as an input or x2 as an input, let's apply scaled version of those inputs to the system. Then if the result is a scaled version of the individual respective outputs, okay, with A and B constants, okay, then this is the so-called the addition property. Okay, so we have the. I mean, I should really say up there multiplication property maybe, just to make it a little easier. Right. So first is the multiplication property. Second is the addition property. And the point about all this is that systems S that have both properties shown above okay, are called linear systems, which means the property of linearity applies to those systems. In effect, what we're really saying is systems of the type that we've shown, they have the property that the output is equal to some scale version of the input for one input systems, or if it's a multiple input system, you know, so this is a what we call a for example, a single input single output system, okay, but what it also says is, you know, you can have multiple input, multiple output. But let's talk about another example. For example, a single output with, let's say, you know, two inputs. So K1 X1 plus K2 X2. So this would be a, you know, two inputs single output, right? So the point is that the output, right, that we're writing as y in this case, can be written as a linear combination, which means scaled versions of the inputs, right? That's what it really says. So how do we use this in a problem? Okay. Well, again, I have some kind of problem to show you how to do this. So let's say we have this, okay? In this problem, you know, it's a simple circuit, and you know, there's different ways of solving this. This is not the only way, but I just want to illustrate the property of linearity to you. So again, it's a simple problem. One input, one output, right? One input, one output. So what this says, okay, again, if we multiply, if we note the input and the output in this case, okay, let's just do that for now. Okay, let's just go and kind of mark it. So let's say our input is this voltage source. Let's call that Vs. Okay, and then our output is this, right? So this is our, and I'll just mark on the side just to make it easy. So Vs is the, sorry about that, let's mark that clean. So Vs is the input. Right, if you think about it, that's your X. And in this case, I10, what we're looking for is the output. That's how we're calling Y. So again, you know, you might not know that this is a linear system, but it is. You know, circuits that are made with resistors, capacitors, inductors, so on, dependent sources, those are actually linear systems. So what that means out of the whole thing is the fact that we can write, you know, y equals something times x, right? So what we know is that really what we can write is something like I10 equals some constant times Vs, right? And this is coming from writing y equals kx, okay? Again, here we have one input, one output, so this kind of thing applies. So whatever Vs is, okay, I10 is a scale version of Vs. That's what it means. And as far as units, you can see that units of K, right, just as an aside, you know, the units of K would be, you know, 1 over ohms, or, you know, mhos. That's just an aside. But, so given any Vs, if you multiply it by K, if we knew what K was, you would get I10, right? So in this relationship, if you know two of the variables between I10, Vs, and K, you could figure out the third one, okay? So that becomes actually the key point. in solving this problem. So you can solve this problem left to right, so you can do some manipulations, but I want to do it a certain way to show you what the kind of the idea is. Now, what I'm going to do in this problem is I'm going to redraw the circuit first, but before doing that, what I'm going to do is start with the point that I'm going to assume a value for I10. Okay, now I'm supposed to find I10. So, I mean, this problem is asking you, what I10 results if Vs is 290? Okay, but I'm going to turn the problem kind of upside down, and what I'm going to say is the following. Suppose I choose a value for I10. Okay, so I'm going to put your problem this way. Okay. So suppose I assume that I10 is equal to 1 amp. Then I can work, you'll see in a second, from right to left to find the value of Vs. Okay, sorry, let me fix that up a little bit. Right? So if I assume I10, right, at 1 amp, I can work from right to left to find the value of Vs that would give 1 amp. Now what does this get me? Well, remember, I10 is kVs, so then K would be equal to, right, I10 over Vs, right? Now I just found K. Well, if I found K, then I can use the equation back with the Vs that was given in the original problem, which is 290. You see what I'm saying? That might be, working from right to left and getting a value might be easier than working from left to right. Again, in this problem, maybe we don't notice it. But that's the point of this problem, is to actually calculate the value of K first, then things will just come out, okay? So the problem is broken down into solving the following problem. Okay, so I'm going to redraw the circuit. I'm going to redraw the circuit first. Okay, so let me redraw the circuit. Okay, and just so that I'm going to do that calculations on the circuit, so I'll draw it a little bigger. So the point in this particular problem, I'm going to try to find the value of Vs, starting from an assumed value of I10, right? Okay, so let me just redraw the circuit first, and then we'll walk through it. Okay, so here's the circuit. Okay, so this is the 20 ohm, 15 ohm, 5 ohm, and the 10 ohm. And what I'm doing is, this is the current that I'm looking for, but what I'm going to do is I'm going to assume a current here. I'm going to assume this is 1 ampere. Okay. So I'm going to assume this, and I'm going to assume the I10, okay? Sorry, I got a phone call. I want to trip to the Bahamas, but I can't go because we have a lecture. All right, sorry about that. All right, so again, now we're going to work from right to left. We're going to work from right to left and find Vs. And the point about all this is that we want to really find K, right? So K is I10 over Vs. And I know what I10 is. I'm assuming what that is. It's 1 amp. So it just comes down to finding what Vs is. So let's just work that through. Now this becomes a circuit problem. It's going to be basically KVL, KCL, Ohm's law. That's what it's going to be. So if we know that I10 is 1 amp, so let's make sure you follow what I'm doing, okay? And I've done this before in previous stuff, and if you look at homework 0, you might see things like that, okay? So if I10 is 1 amp, then the voltage across the 10 ohm resistor is 10 volts by Ohm's law. Okay, furthermore, this current I10 is also flowing through the 15 ohm resistor like this, so the voltage across the 15 ohm is 15 volts, also by Ohm's law. Now if you look at the right loop, okay, if you look at the right loop which contains a 5 ohm, the 15 ohm, and 10 ohm, you see that the voltage across the 5 volt resistor, okay, the voltage across a 5 volt resistor has to be 25 volts by KVL, right? Because you have to have a rise of 25 volts and then drop of 15, drop of 10 to balance it if you go in the clockwise direction, right? So you can see this right away. It's got to be 25 volts. Well, if the voltage across a 5 ohm is 25 volts, then the current to the 5 ohm, top to bottom, right? This current right here has to be 5 amps, right? So if that's 5 amps, then the current that's flowing through the 20 ohm coming to the junction, like this, right? This must be 6 amps. And therefore the voltage across the 20 ohm by Ohm's law has to be 120 volts, right? Now if you look at the KVL on the left side, okay, so KVL on the left side, you see that Vs is equal to 120 plus 25, which is equal to 145 volts, right? So what this is saying to me is that if Vs was 145 volts, I10 would be 1 amp, right? So let's just go and find K, right? So K is equal to I10 over Vs, right? I10, I assume, was 1 amp, and then Vs is 145 volts, right? So this is the value of K. But the thing is, for the system above, okay, this is always true, right? So the question becomes, suppose I make Vs 290 volts. Okay, that's what it is in the original problem. So basically what that's saying is that suppose I double Vs. Well, if you double Vs, you're going to double the current, right? That's what I is equal to K times Vs is telling you. So what we have is now, because we found K, what that means is, in general, for this circuit, for any given Vs, okay, I10 is equal to, okay, K times Vs, or basically, 1 amp divided by 145 volts, that's the scaling factor, times Vs. So you give me the value of Vs, and I tell you what I10 is. So going back, in the original problem, Vs is 290, if you look over here, and that's conveniently chosen as twice the value of 145. But it could have been anything, really, it could have been really anything. So again, let me just write over here, get back to the, so for original problem, Vs was 290 volts, which means I10 is equal to 1 amp divided by 145 volts, or I could have just written, 1/145 times 290 volts. I just want to show you that this volt and this volt cancels, leaving you behind amps actually, right? So 290 over 145 is 2, so the result is 2 amps. Okay? I mean, you could do this problem different ways. You should try to do it to make sure you get 2 amps. But this is the point about linearity. Okay, so linearity, scaling factor, all that kind of stuff. So we can actually use it to our advantage. Try it different ways. See how you like it. I mean, you can try, for example, source transformation. Go to the original problem, do source transformation, working from left to right. and try to find a current through I-10. See what happens. See how the numbers come out. See if the multiplications, additions, subtractions, etc. are easier or tougher. Okay. But again, I just wanted to point this out to you. This is a short lecture. We talked about linearity before, but this is in essence kind of what we mean, what we're talking about. Thank you very much, and I will see you next time.